So this is the research team that contributed to this basically work, this research. The topic of my talk is development of advanced robotics system. And basically, I'm part of two research centers at KU that is responsible for this research work. A quick word about Jamiat Khalifa. It's research-focused university. Okay, so although we stress teaching, but our faculty members, for example, have very light teaching load compared to other universities. It's highly ranked worldwide, ranked 211 worldwide according to QS World, and it offers bachelor, masters, and PhD. So I encourage you to apply and hopefully be part of our research family in the future. We have good number of specialized research centers at our university. The outline of the talk, I'll briefly touch on the applications of robotics, and I would like to compare between the pillars of robotics, the parallel and serial robots, and I'll talk about the methodology of developing robotic systems, and then I'll talk about a number of examples of research that my group is doing, and basically give also a brief of Mohammed bin Zayed robotics, international robotics competition, to encourage you actually to be part of our future competition, because it's highly basically popular and it could grow you very much so. And then I'll conclude with some points. Robotics applications probably stems from, or in so many fields, from surgery to logistics to security. So it became very popular even to have it as a household part for vacuum cleaning, for example, or window cleaning. So it's being popularized at a very high rate in so many areas. One of them is industry, and particularly in manufacturing, which is the area that I'm focusing on. In terms of manufacturing, there are big number of applications from assembly, machining, manufacturing, etc. My work is mostly focused on developing robotic system for machining applications, like CNC machines, computer-animated machines, and additive manufacturing, where you 3D print, for example, structures. And I'll show an example of that. Many of us are familiar with the example on the left, actually, the serial robot, okay, where basically links are connected serially to each other, okay. My focus more is on the system on the right, which is parallel kinematics, or a hybrid system, which combines basically the advantages of both. Here I'm comparing the advantages and disadvantages of serial and parallel robots, okay. For example, the workspace for serial robots, traditional robots, is quite large, while for parallel robots, it's quite small. However, you have very high stiffness, very high accuracy. So the best thing is to kind of combine between the parallel and serial to come up with a new breed of robotic system that marriage the advantages of both. And this is what we are doing in many of our basically developments. For example, the one on the left is a serial CNC machine, the traditional CNC machine, and the one on the right here, a robotic serial system, of course. Okay, here it shows parallel kinematic robotic system, different examples from the industry, from hexapod, the one in the center top here that has 6 degree freedom, to basically some spindle control here that has only 3 degrees freedom, for example. Okay. The hybrid kinematic machines, again, they are finding more and more usage in the industry. The triceps at the top here with different variations, and basically you have a number of again, hybrid kinematic machines in the bottom part of this screen. So roadmap to conceptualize new machines, how we go about doing that. So the way we do it is we synthesize the structure. So we determine how many degrees of freedom we need for our application, for example. And based on that, we try to basically identify and enumerate what types of mechanisms are there that will satisfy these degrees of freedom. So then we formulate the post kinematics and differential kinematics for these new concepts. and based on a number of performance measures I'll show in a minute. For example, workspace, stiffness, accuracy. Based on that, we'll evaluate these different competing mechanisms. And then we'll go through optimization process to optimize the geometric, basically, dimensions of this mechanism that we'd like to fabricate and prototype. Then we'll start the prototyping process. And then we go through the formation of dynamic parameters, because however basically how hard you try to make sure that your dynamic parameters are accurate, it's difficult to be exact in computing the inertia or the mass of the different fabricated components. So we need to resort to experimental work, such as impact hammer test or similar tests to identify different dynamic parameters. Then we'll go through the phase of the control design. Okay, basically tailor the control algorithm based on the application again, and to get the maximum out of the mechanism that we are building, we need to calibrate المعايرة, okay, calibration of the system in order to give you the accuracy that you anticipated. The performance measures, for example, could be the accuracy, الدقة of these mechanisms, repeatability, the stiffness, especially if we are talking about machining, then stiffness becomes very important. Manipulability, how basically the range of motions that we have for this mechanism, for example. Singularity avoidance, for example, in serial robots, the singularity means that you lose a degrees of freedom. For example, if all the links are aligned, okay, with each other, you cannot move basically along that aligned direction. So that's a loss of degree of freedom. However, in parallel kinematics, it's the gain of a degree of freedom. For example, if some of all the legs are parallel, then okay, the whole platform will start moving without any control. So you have to ensure that you don't go through singularity for such mechanism. Also, the issues of sizing of the workspace, because you need to buy a machine, but of course it's justifiable to have reasonable sized workspace for any machine that you have. Design optimization. Okay, so you have to decide on the algorithms that you'll be using for the optimization. For example, if I want to have high workspace or big workspace, high accuracy, basically certain number of degrees of freedom, then you'll enter that through a multi-objective, basically optimization algorithm or function in order to iterate until you find the best optimal solution that satisfies these all different objectives. Okay, so this is part of the process that we go through to design the systems. Dynamic modeling, again, initially you'll have some rough estimate of the different parameters of inertia, mass, friction, etc. However, to exactly identify what are the values of these different parameters, you have to go through some experimental work, okay, to identify these different parameters accurately, because that will impact controls and how good you are able to manipulate your system. So this is a process that one have to go through. In our case, we developed this hybrid mechanism in which we combine two planar mechanisms. For example, this is the mechanism, the lower part, it has 3 degrees of freedom, namely X, Y, and rotation only. By marrying these two in this format, then you'll have 6 degrees of freedom. One is redundant, which is along the green direction. Okay, so you end up with effectively 5 degrees of freedom system. Okay, the purpose is to be able to tailor the shape of the machine, the degrees of freedom that you want, based on the needs of the user. So one can substitute one of these manipulators, for example, with just 2 rotary axis table. Okay, so it's highly tailorable. One can basically reconfigure it as he or she desires, basically. So this is the machine that we built in our lab that has 5 degrees of freedom, as I said. Again, the top part carries the spindle and has 3 degrees freedom. The lower part carries the work table that carries the workpiece that you would like to machine. And we are using in this machine basically linear motors. It shows the machine moving. So it's linear motor, meaning motors that you are used to is rotary motors, where you have spindle rotating. So by opening the motor, so the stator is flat, and the rotor now is moving along that stator. Okay, so you'll have these linear motors that's shown at the bottom of the machine. Then you have very high accuracy, direct coupling. There's no need for gearboxing. But it's a bit more challenging to control, but this is part of research work that we are doing. Also the video in the top right here shows the machine doing some machining tests on our piece. And basically the other video shows the different degrees of freedom that the machine is capable of doing. So here both tables are moving together, if need to. And the nice thing about this concept, you can elongate the machine as you want. It can be like 50 meters long if you want, for example, to machine aerospace parts. So you can extend it as much as you want. After building the machine, of course, you have to go through kinematic calibration to identify exactly, for example, if I machined one of the legs to be 300 millimeters in length. Okay, when I machine it, it came out to be 300.13 millimeters. So that basically difference will impact the final accuracy. So the kinematic calibration role is to identify exactly these geometric values, okay, to 3 decimal or 4 decimal places in order to be able to estimate the location in a very accurate fashion when we are running the machine. Okay, so that's the purpose of the kinematic calibration in general. Okay, and there are a number of methods for calibration. There is external calibration where you resort to some external viewpoint to identify the X, Y, Z of the end effector, for example. Or you can have auto calibration where the machine itself can go to pre-specified point and self-calibrate itself. So there are multiple methods, and we use in our system external calibration methods. Okay, and usually once you have data out of this calibration method, you'll start with the modeling of the machine, then doing these measurements, then an estimation of the unidentified values, and then if there is a need to correct, you can do a number of iterations after that. Okay, so this is the external calibration. You'll have a laser tracker system to observe where is the end effector. So it will give you basically X, Y, Z in a very accurate fashion that you can basically plug into your kinematic models to identify what are the unknowns, or basically not completely unknown, but there is some indeterministic values associated with them. Okay, so then you'll go, once you have calibrated the machine and you are confident about the kinematic values, then you can go through designing certain control strategy to give you basically proper profiling or accurate positioning. So based on what's required, you can design a control algorithm based on that. Okay, and usually in our case, for example, for machining certain part, we'd like to have the end effector position very accurate. That's X, Y, and Z. While in our case, we are controlling the position of the legs. So there is a mapping between the task space and the joint space. So this is the role of a control strategy to try to do this mapping and to come up with the proper control signals to basically coordinate the motions of these different motors to give you an accurate profile or end effector positions. Again, this is a simplified model of the different components that we use in our system. The lower right, it's the linear motor that we use. You have to have certain drives to drive these motors, and then you have a controller, a Galil controller in our case, to coordinate the motion between these different drives to give you the end effector positioning that you are interested in. Okay. Again, this is basically the control panel. And I would like to emphasize that everything that you see here was developed in our lab. So the students did this, okay? Even the machining was done in our machining lab in the university. So basically it's a complete in-house product, the machine that we saw earlier. And of course, in order to be able to control the machine as a CNC machine, you need a graphical user interface that mimics traditional machines. And basically, this also was developed for this particular machine in order to control it as basically simple as a traditional machine tool. Again, this was developed in our lab. Okay, we can move from that concept to something like this. Okay, so this is a conceptualizing of future projects that similar to what we had, but that will give you more extension and different types of degrees of freedom. And here where reconfigurability plays a big role. Okay, so this is an example. Actually, this is an old machine that I developed during my PhD work at University of Illinois Urbana-Champaign, where it has basically translational degrees of freedom, X, Y, and Z. There's no rotations. And it was used actually by Oak Ridge National Lab in the States. And later it was used by Caterpillar company which I worked for actually for a number of years. Okay, so the beauty of this, it was driven by hydraulics and the spindle was ultrasonic, so it can drill brittle material without shattering it. So that was the distinctive part of this machine. This is another project that currently we are working on, a cable-driven robot. So by controlling basically number of cables length, we'll be able to control the positioning of the connected point, the end effector. Why we are using it? We'll be using it for 3D printing of structures, meaning we would like to build small villa or basically small structures, okay, using the cable-driven robots. Okay, so we'll have quickly sitting cement, and cables will be moving the protruding head, okay, according to an architectural plan to erect a machine or erect a building based on the plan. Okay, so this is one of the projects that a couple of students are working on, PhD and masters. Another project is to construct walls by drones. Okay, so usually, basically, you have these bricks that you have to assemble together in order to build a big wall. Okay, this is a project where master students working to pick and place bricks. So he has to basically develop the control algorithms, the gripper, etc. and has some artificial intelligence to hold the part and basically put it in the proper location. Okay. And this is basically mobile robot for machine. This is not our robot, but this is being used outside. Okay, developed in Germany. We would like to develop something similar where you have this mobile system that is able to basically move and reconfigure itself based on the basically surroundings. So this is a project that very important to our research group that we are working on right now. So in this particular application, we would like to develop systems that enable us to basically, instead of bringing a bridge to the machine, rather we'll have the machine basically going and reconfiguring itself based on the requirements over there. Somehow the application window is not seeing it. I was going just to talk about Mohammed bin Zayed International Robotics Competition at Khalifa University. Basically, it's held every 2 years, and the awards reach total awards like $5 million, and it has number of challenges. Okay, for example, 3 different challenges last time, and it basically attract a good number of teams some international, from all over the world. Okay, so I would like to encourage you to start looking into these in a very serious fashion, because I think our students in the Arab world are capable, and if they put their mind into it, I'm sure they can compete at that international stage and be able to make us all proud. And it's lucrative in terms of the amounts of basically the awards. So even few students could form a team or a company even, and focus on satisfying the requirements and being able to perform well, and that could lead to really pretty basically positive results for them in terms of income as a company. I had a number of videos to show, but it seems that this is not working at this point. So I'll jump to the final conclusion page. Okay, so at last I would like to say that design of new systems includes structural synthesis, design optimization, system identification, control design, and calibration. So it's a holistic approach to develop such systems. The selection of performance measures to be optimized depends on the significance to application. For example, if I would like to have machining, I'll focus on accuracy. If you have assembly, maybe it's less accuracy, more workspace. So you have to identify the proper measures that you have to optimize based on the application. We have developed a number of basically robotic systems in our lab, and it's basically targeting applications that needed by the local industry or community. More regional effort is needed in the areas of design and development of advanced systems. And here I'm talking about advanced systems in general, related to IoT, to robotics, to any basically real development, because we lack that at this point. We are just focusing on consuming good products from the West. I think we have to have a tipping point where we shift to more being contributor to such efforts, and I'm sure we are capable and we have the critical mass to make any such startup be successful. And our next step actually to look into spin-offs of some of these concepts that we are developing in our lab. I'm done. I'm sorry for the inconvenience of the technical issues with the video in the last couple of slides, but I hope my points came through. And again, please be part of our teams in the future, Khalifa team, or participating in the Mohammed bin Zayed International Robotics Competition. Okay, we'd like to see you basically on these international stages time and time again.